So in this section, we're going to be continuing our triangle congruence proofs using two new possibilities. That's going to be angle side angle and angle angle side. To add one new definition first, an included side of a triangle is a side that's between two angles that are given. So we have an included side, it looks like, in both of those next couple diagrams. Because if I want to describe a new way of proving triangles are congruent called the angle side angle postulate, or again ASA for short, kind of like how the triangle looks, we have two angles and then the side in between the name. That means that if I have two angles and the included side, so again that side in between those two angles from one triangle, and that's congruent to those same three things, I guess, two angles and then that same included side from another, that's proof that the triangles are congruent. So in this case, if it looks like I have angles A and C that are congruent to angle D and F, and that side that's included between the two, AC and DF, is also marked congruent, that is going to be a proof that those two triangles are also congruent as a whole. If we're then given a question to decide which triangles are congruent by this new property, angle side angle, we just have to examine the evidence that we're given in the diagrams. So in our first case, it looks like we have two angles and the included side marked congruent, so that's a good start. Again, angle side angle, just like the name, should have two angles with a side going in between the two. Looks like we also have the situation going on in a separate triangle, so again, two angles marked congruent with that side included between the two marked congruent as well. But if I look at this third case, it looks like we have the angle that's marked, or sorry, the side rather that's marked congruent is not the included side. So let's look at what we can prove. We can prove that the first two triangles, SUV and NEO, notice with the naming as well, if I'm to make a congruency statement with those, SUV is the unmarked angle, angle 1, and then angle 2 in terms of those tick marks, and then keeping that order the same, unmarked 1 tick mark, 2 tick marks, that's NEO. Matching in that same order. Those are congruent again because those do match our pieces from our ASA postulate. We have two angles marked congruent, and then that side that's marked congruent is also in between. If I was to look at that third case though, I would need an adjustment for this to be true, so I would need some different starting information. TW is the included side, so that would have to be the congruent side, marked congruent to those EO and UV from our other two triangles. Since I'm given AW instead, that's a non-included side, we wouldn't be able to mark that that is congruent using our new postulate. We can also use two angles and a side to mark triangles congruent in a different configuration. That would be an angle-angle side theorem. And angle-angle side is telling me that if I have two angles and then this time the non-included side of a triangle, so now we're thinking again just the side not in between those two angles, is going to be congruent to two angles in that same corresponding non-included side from another. That is going to be another proof that these triangles are congruent. So notice from before, if I was going for angle side angle, I would need, for example, like AB to be marked congruent. But as long as I have a non-included side and a non-included side in that separate triangle marked congruent, notice that it does need to be across from that same angle. So opposite from angle E, opposite from angle B, since those angles are congruent. If that is a corresponding non-included side, again, I can't use something like BC for one triangle and DF for the other because I'm across from different angles. That will be a proof that these triangles are congruent. So again, same angle, matching across that same non-included side. That is going to be proof as long as I have two angles and that non-included. If I was to work through a proof using this new information, I would work same as with a lot of our proofs, just from the diagram itself and also just going step by step to see what we can prove. Using the given statement, it looks like that's already marked in the figure for us. So M and K mark congruent, and it looks like these sides, MW and, or I guess WM, doesn't matter, and RK are marked parallel as well with that kind of play looking symbol. We just want to make a step first and just take that for granted that that is going to be our given information. So our general strategy, if I'm looking to prove that these two triangles are congruent, looks like this triangle and this one, WMR and RKW, as long as I can find three pieces of evidence, just like in our last section, that will count. So we're looking for three congruencies, and now that we've added on two new proofs, we can look for angle-angle side or angle-side angle. So it looks like I start with one pair of angles, and if I'm looking for anything else that I can use from this given statement, I can't expand too much on that congruency statement because it's almost written as is. Yeah, can't do anything with that. But if I know that these two lines are parallel, we can use that to definitely get a next step. And again, if I'm extending parallel lines, this may help you to see with this transversal running in between the two. But it looks like we do have a pair of angles we can also mark congruent that aren't marked yet. It looks like these angles in these opposite corners. Again, if we are comfortable with our terminology, we know that we're going to call those alternate interior. It looks like those angles are going to be congruent. So again, that's a good start if we're trying to prove these two triangles match. We have two angles, it looks like, that match as pairs. We had the given and we had these new alternate interior. So now if I'm looking for one more piece of evidence, I can use the shape of the figure itself. It looks like if I have just the side running in between the two, notice that that's a pretty common start to a lot of our questions. If the side is shared between those two triangles, we know that that side is going to be congruent to itself. And that rule that tells us a segment, or really any geometric figure, is congruent to itself is going to be that reflexive property. So now that I've added in those information, again, I think this helps if we mark it up in the figure itself. We can examine what kind of congruencies we have, and that may be enough for one of our triangle proofs. So we started with one pair of angles from the given. We started with a second pair of angles, as long as I figured out those were alternate interior. We added in that reflexive shared side through the center. So it looks like if I have two angles, and it looks like this is this corresponding non-included side. Notice it is across from this angle marked with one congruency marking for both, so I don't have different sides from different triangles. This looks like we do have a proof. We have two angles and the side that's not included. That would be our new angle side proof. So to try this with another example, we're going to be taking very similar steps. Again, our goal is basically to show that if I want triangles to match, I need three pieces of congruency, and those three pieces of congruency can, remember, now include two angles and a side that's either included or not included. We're just going to have to find out. So we are given one congruency at the beginning. Again, that's a nice start. We have that marked in the diagram as well. If we're also given this information that we have a bisector, let's mark that as a given, because that, again, may play into our next step. Just like with any other second step of a proof, we've said pretty much all we can about S and Q. We already know they're congruent, so I don't want to expand on that. But if I'm told that we have an angle bisector, that may help again to prove congruency, because just the fact that a bisector is not important. We want to use the fact that things are congruent based on that bisector. That's going to add us evidence to prove those two triangles match. So if I know that we do have a bisector, again, RP bisects SRQ, we do want to be careful which angle is bisected. Some people might say that like we could cut this angle at the top in half, but if SRQ was the angle that was being bisected, again, cut in half for our purposes, that means that we could mark these two angles at the bottom congruent. Again, if that was being bisected, only way it could bisect it is if I cut those into two congruent angles. And now I just want to use that for a next statement, because again, if I'm able to find three pieces of congruency, finding those second pairs of angles that match is a great start to this question. So you do want to be careful how you name this. Again, SRP, QRP. You could reverse the names and say something like PRS, PRQ. As long as we name the angles with R as that vertex in between, that is going to be our second congruency. Can't just say R and R, notice, because that's two angles at that same vertex. But I just said something that something along the lines of, if I have an angle bisector, that's just showing that we have those two congruent angles. And much like our last situation, it looks like we do have a shared side going through the center of this figure. Really common start to a lot of our diagrams, so it's going to be something pretty common to use in a proof. And we can use basically the same idea as before. If I know that we're using that same side in two different triangles, this is the rule that tells us a side is congruent to itself. We know that RP, again, is going to match itself. There's no way it really can't. And that means that if it's congruent to itself by that reflexive property, again, something just matches itself, that means that now we have three pieces of congruency. That may be enough for a triangle proof as long as it's in one of our accepted orders. Looks like we have two angles from one, two angles from another that match. And again, this side that's not included, it looks like is across from the same angle, so that would be the same corresponding side. Looks like that is enough evidence to prove those two triangles are congruent. And this is another case where we're using that angle side postulate. We haven't used angle side angle because, again, we haven't found angles that are included between our known angles, or sorry, sides that are included to be congruent. But as long as I have that two angles, and then the side that is, again, across from that same angle in both, that is going to be a proof that those triangles are congruent. I find three pieces. Those three pieces are in the right order. And our next problem, problem 3, is kind of calling back to that earlier problem asking about if I have three pieces marked congruent, we don't want to automatically assume that those triangles are going to match, because again, those three pieces have to be in one of our accepted orders from our theorems. And if it looks like I have two angles and a side, and even that side looks not included, a lot of people might be kind of leaning towards answer C here. Looks like we have two angles, not included side, two angles, not included side. But we've got to be careful. Again, it's very important that we have that same corresponding side in both triangles. It looks like in the first triangle, the side is opposite of our angle marked with two congruency markings. But in our second triangle, that same side that's marked congruent is opposite from a different angle. So since that's not what we call a corresponding side, looks like our answer here is instead going to be B. So this is a case saying that to watch out, even if I have two angles and a not included side, if I have two angles but that same side is not in that same location, we're not going to be able to prove that those triangles are congruent. So in our part B, it looks like we have another figure to consider, and it looks like we have even less to go on in the last case. We only have two pieces marked congruent from each, and if you're thinking that we need three to prove a triangle, you'd be right. Although I think we do have enough evidence here. If we notice this kind of a bow tie, or if I was to turn on its side, hourglass shape is going to be a pretty common start to our questions. Because if I use the fact that these vertical angles in the center are congruent, it looks like we may have enough evidence because now I have three pieces marked congruent. And let's see if that matches one of our statements. So yeah, if I use the fact that those angles are vertical, that adds one more piece of congruency. And it looks like in this case, if I have two angles, and that same non-included side, notice it's important from that last question. The side that we're given is across from the angle marked with one congruency marking. So it is that corresponding side rather from both triangles. It looks like we do have evidence by angle, side, two angles congruent. That same corresponding side that's not included is also congruent. That is going to be enough to prove that these triangles match. Our next question type kind of leaves this open to us again. It looks like we have three pieces marked congruent, which is a good start, but again, I do have to make sure they're in a certain configuration. It looks like we have two angles marked congruent, two angles marked congruent, so I'm thinking this is either going to be angle, side, or angle, side, angle. And remember, the only difference between those two is basically the location of your side that's marked congruent. It looks like the side that is marked congruent runs between those two angles, so whenever I think between, I think included, and I think just like the name itself, that side running between those two angles means that our first case is going to be a case that I'm using my angle, side, angle postulate. I'm not using angle, side because, again, that side is going between the two angles. It's not going to be what we call non-included. If I was to examine the second situation, it looks like we have, again, two angles marked congruent. If it's a right angle, that's still essentially a congruency marking. But this time it looks like the side that's marked congruent is not running in between those two angles, which is still fine. Notice that it's still opposite my right angle. We call that hypotenuse from both triangles that's marked congruent. So this would be our other theorem, but it looks like that's still enough evidence. Two angles in the not included side, as long as that side is the same in both triangles, same as in corresponding, that is going to be another reason we can prove these triangles congruent. And lastly, we have some error analysis. So it looks like our student or somebody has answered this question, said that these triangles are congruent by angle, side, angle, which looks like it works in at least one of these cases. We have two angles and then that included side running between those two angles marked congruent. But if I was to examine the second situation, again, this is not matching my information from the other. It looks like this is going more for an angle, side proof in that we have the side that's not included that's being given. So I would say in this case, the error that's made is that if I was to try to use angle, side, angle, that specific proof, I would need to know that between N and L, those two given angles, that would need to be my included side. So since that side does not run in between my two angles that are given, I wouldn't be able to use ASA. And again, I wouldn't be able to use angle, side, angle either because I don't have that matching situation in my second triangle. Is basically like the first one going for angle, side, next one going for angle, side, angle. If those don't quite agree with each other, it looks like we're not going to be able to mark that those are congruent.